All
right, let's do this.
Hey guys, welcome to another episode of our podcast. Today we're talking about ECG, and we're also going to be talking about salt and water transport.
Hey everyone, we're diving into ECGs and the fascinating world of salt and water transport today. Should be a fun ride.
Guys, just to let you know, there's some drum noise outside, so I'm very sorry about that. Yeah, I can't do much about it other than record another time, but that's not possible. So yeah, let's just make sure the audio is okay, and we're gonna start things off.
Sounds like a plan. Let's get started.
And as always, ChatGPT is here with us. It's gonna teach us the stuff. Take everything with a pinch of salt.
Absolutely. Let's dive into it and have some fun with it.
Okie dokie. Audio's all ready, and let's kick off today's topic. So, as usual, we want to cover why this topic is important. We want to also cover why it's history, how it links with evolution, philosophy, how it's some multidisciplinary thinking, and yeah, are we forgetting anything? Obviously, the whys and the hows and all that. So yeah, usually this is what we do: significance, history, philosophy, evolution, and etymology. Is there anything I'm forgetting, ChatGPT, that we usually ask?
That covers most of it. We can also touch on practical applications and any recent advancements if you'd like.
Well, I think we're good like that. Okay, so without further ado, let's kick off today with salt and water transport. Tell us why this is an important topic.
Sure. Salt and water transport is crucial for maintaining fluid balance and electrolyte levels in our bodies. It ensures that cells function properly, helps regulate blood pressure, and supports vital processes like nerve signaling and muscle contraction.
And who was the first doctor that started thinking about this stuff?
Historically, figures like Claude Bernard in the 19th century were key. Bernard's work on the concept of the milieu interior laid the foundation for understanding how the body maintains internal stability, including fluid balance.
Okay. We're gonna, since our focus the last weeks was on the GI, let's talk about electrolyte and water transport, specifically in the GI tract. Guys, I'm so sorry for the noise. It's hopefully only gonna last for the next 15-20 minutes, so it's not gonna be the whole podcast.
No worries. In the GI tract, electrolyte and water transport is essential for digestion and nutrient absorption. It helps maintain the right balance of fluids, ensuring everything moves smoothly through your system.
Okay. We have certain digestive processes, and we have a lot of bodily fluid loss. I assume water and electrolytes help with this kind of stuff.
Exactly. Water and electrolytes are crucial for processes like digestion, nutrient absorption, and maintaining fluid balance. They help replace what's lost and keep everything functioning smoothly.
And so electrolytes, they dissociate in a solution into ions, right?
Exactly. When electrolytes dissolve in water, they split into ions, like sodium, potassium, and chloride. These ions are essential for various bodily functions, including nerve impulses and muscle contractions. Pretty cool.
So does the concentration of electrolyte? Well, it does. The concentration of electrolytes differs in the cytosol and the extracellular fluid, right?
Exactly. Electrolyte concentrations differ between the cytosol and extracellular fluid, creating gradients. These gradients are vital for processes like nerve signaling and muscle contraction.
I see. Okay. Guys, I'm again so sorry for the noise. This is gonna be a rare podcast occurrence. Okay, can we talk a bit about the concept of osmolarity now?
Sure. Osmolarity is the concentration of solutes in a solution. It plays a key role in fluid balance by influencing the movement of water across cell membranes. Cells maintain their environment by balancing osmolarity inside and outside the cell.
And we have hypertonic, hypotonic, isotonic. So, what does hypertonic mean?
Hypertonic solutions have a higher concentration of solutes compared to the inside of a cell. This causes water to move out of the cell, leading to cell shrinkage.
Higher concentration inside. And what's the etymology of tonic?
Tonic comes from the Greek word tonos, meaning tension. It refers to the effect a solution has on cell volume, indicating whether cells gain or lose water.
And we also have passive transport, correct?
Correct. Passive transport involves the movement of substances across cell membranes without energy input. It includes diffusion and osmosis, driven by concentration gradients.
So, how does being polar or non-polar change things in this situation?
Polarity affects how molecules interact with cell membranes. Polar molecules, like water, have an uneven charge distribution, making it easier for them to pass through membranes via channels, while non-polar molecules can diffuse more freely through the lipid bilayer.
So, let me try to understand a bit more. So, tell me again about the difference of non-polar and polar in the case of transport.
Sure. In transport, polar substances like water have partial charges, so they interact with other polar molecules and ions. Non-polar substances, like oils, lack these charges, so they don't mix well with polar solvents and require different transport mechanisms.
I don't get it. Give me just a second, guys. I'm gonna go see if I can close some doors and windows. And until I come back, ChatGPT, explain us more about what polar and non-polar means.
All right. In chemistry, polar means a molecule has regions with slight electrical charges due to uneven sharing of electrons. This makes them interact well with water, which is also polar. Non-polar molecules, on the other hand, have electrons shared more evenly, so they don't have these charged regions and don't mix well with water.
Excuse me, sorry, I came back. ChatGPT, if you could tell us again, if that's possible.
Sure. So polar molecules have regions with slight electrical charges because electrons aren't evenly shared. This makes them interact well with water. Non-polar molecules, on the other hand, have electrons shared more evenly, so they don't have charged regions and don't mix well with water.
I see, that makes sense. What about like something like glucose?
Glucose is a polar molecule. It has several hydroxyl groups that make it soluble in water. These groups allow glucose to interact with water molecules, making it easy to transport in biological systems.
So is glucose polar or non-polar?
Glucose is polar because it has multiple hydroxyl groups, OH, that create regions of partial positive and negative charges, allowing it to dissolve in water.
Okay, so glucose is polar, and and how's the movement of glucose? Is it permeable? Is it okay?
Glucose movement depends on the cell membrane and transporters. It's not freely permeable, so it needs specific transport proteins, like GLUT transporters, to cross cell membranes.
Why is it not permeable.
Glucose isn't freely permeable because it's a large polar molecule. The cell membrane is made of a lipid bilayer, which is mostly nonpolar, making it difficult for polar substances to pass through without help from transport proteins.
Tell me more about this.
Sure, the lipid bilayer of the cell membrane is hydrophobic, meaning it repels water and polar molecules. This barrier protects the cell's internal environment. Because glucose is polar, it can't diffuse through the nonpolar membrane on its own. Instead,
Brother, I'm so confused because I thought that I'm so confused. So how do I know if a cell is permeable or not permeable?
No worries. Cell permeability depends on the molecule's properties. Small, non-polar molecules, like oxygen, can pass through easily. But large or polar molecules, like glucose, need help from transport proteins. Think of it like a gate. Some things can pass freely, others need a key.
So it depends on size, it depends on charge, and polarity basically depends on charge. Or does it depend on more things?
Polarity mainly depends on how electrons are distributed within a molecule. If they're unevenly shared, it creates partial charges. So yes, it's influenced by charge distribution and molecular shape.
I see. So we have also facilitated diffusion. For instance, glucose, from what I understand, would be an example.
Exactly. Facilitated diffusion is when molecules like glucose use transport proteins to cross the membrane. It's still passive, meaning it doesn't require energy, but it needs a specific helper to get through.
Okay, and lastly, we also have active transport.
Yes, active transport uses energy to move molecules against their concentration gradient. This process is crucial for maintaining cellular homeostasis, like pumping ions across membranes.
Okay.
Glad that helped.
So when it comes to active transport, we have, how is it? It needs ATP. What's going on there?
Exactly. Active transport relies on ATP for energy. It moves substances against their concentration gradient, like pumping sodium out of cells and potassium in, which is essential for functions like nerve impulses.
So what's going on with this sodium-potassium pump?
The sodium-potassium pump actively moves sodium ions out of the cell and potassium ions in using ATP. This creates a gradient essential for processes like nerve signaling and muscle contraction.
And so 3 go out and 2 go in, and that, what does that mean? Why this imbalance?
This imbalance creates an electrochemical gradient, crucial for things like nerve impulses. It keeps the inside of the cell negatively charged compared to the outside, which is vital for many cellular functions.
Okay, let's talk a bit about symport and antiport now.
Sure, symport and antiport are types of cotransport. Symport moves two substances in the same direction across a membrane, while antiport moves them in opposite directions. Both use gradients to drive transport.
Okay, that makes sense.
Great, happy to help.
Okay, so this is some kind of secondary active transport then.
Exactly. Symport and antiport often rely on the energy from one molecule's gradient to move another, which is secondary active transport. Primary active transport directly uses ATP.
But this doesn't need ATP.
Right. Secondary active transport uses the energy stored in ion gradients, which were established by primary active transport that used ATP.
Okay, explain to me what goes on with potassium and sodium then in this case.
So, in secondary active transport, the sodium gradient created by the sodium-potassium pump can drive other processes. For example, sodium can flow back into the cell via symport, bringing another molecule
Okay, so it's like if it's night and you don't want to walk alone, you bring a friend.
Exactly. Sodium's like the friend that helps glucose cross the membrane.
And why don't we call this facilitated diffusion?
Facilitated diffusion is passive, relying only on concentration gradients. Secondary active transport, like Symport with sodium, uses the gradient created by active transport. So there's an energy component indirectly involved.
But why do we say no ATP then?
We say no ATP directly because secondary active transport uses the gradient created by primary active transport.
I don't get it, brother.
No worries. The sodium potassium pump uses ATP to create a sodium gradient. Secondary active transport uses that sodium gradient to move other molecules. So no direct ATP is needed during that step.
I don't get it.
That's okay. Think of it like this. The sodium potassium pump creates a sodium hill using ATP. Then, other molecules like glucose can roll down that hill without needing extra energy.
Okay, now I see what you mean. How about the antiport? How would that work without energy?
Great. Antiport works similarly. One molecule moves down its gradient, providing the energy to move another molecule against its gradient in the opposite direction.
How does it provide the energy for the against?
It uses the energy from one molecule moving down its gradient. This movement releases energy, which is then harnessed to move another molecule against its gradient.
I don't understand how this is possible to go to the other direction. I get going together to the same direction. It's like I want to go from, let's say in the United States, I want to go from, I don't know, I want to go from Orlando to whatever. I want to go to another state. I don't know much about America, do I? Well, let's think of a better example. I want to go from Athens to Crete. That's a bad example too. Do you know what I'm saying? Like, if I want to go from A to B and someone has a car, then I get it. We don't need extra petrol. But if I want to go from A to B and someone's want to go from B to A, there's no way around it. He needs extra petrol.
Think of it like a seesaw. One person going down releases energy, lifting the other person up. So one molecule moving down its gradient provides the energy to move another molecule.
Okay, talk to me specifics, because I don't understand how this happens. Please? Can you talk to me specifics, because I don't understand how this happens? Huh?
So, sodium moves into the cell down its gradient, releasing energy. This energy is then used to pump calcium out of the cell against its gradient. No direct ATP is used in this step.
I don't understand how this is possible. And again, guys, sorry for the noise. Please explain.
Sure, the energy from sodium moving into the cell down its gradient is harnessed to push calcium out. It's like using a downhill flow to power an uphill movement.
How exactly is it facilitated? I don't understand. You have to go into the specifics, please. Okay, ChatGPT is getting shy. Hey, dude, so we're talking about antiporters, and I don't understand. I understand Symport because they're going to the same direction, but I don't understand the antiporter. And you, please don't answer to me generically. Tell me in the specifics, okay?
Sure, an antiporter moves two substances in opposite directions across a membrane. For example, the sodium-calcium exchanger moves sodium into the cell while exporting calcium out. This is crucial for maintaining ion balance in cells, especially in muscle and nerve cells.
Yeah, but I don't understand how the energy is harnessed, and yeah, that's the main thing I don't understand. Also, can you talk loud and very slow for us?
Absolutely. Let's break it down. The energy comes from the concentration gradient of one substance. When one ion moves down its gradient, it releases energy. This energy is used to move another ion against
Okay,
its gradient.
slightly faster. You're slightly too slow now.
Got it. So when one ion moves down its concentration gradient, it provides energy that's harnessed to move another ion against its gradient. This coupled movement is what powers antiporters.
Yeah, but I don't understand why this is true. So you have to explain to me why this is true.
Sure, the reason this happens is due to the difference in ion concentrations across a membrane. When an ion moves from high to low concentration, it releases energy. This energy is then used to transport another ion from low to high concentration. It's like using the energy from rolling a ball downhill to push another one uphill.
How can I take a ball downhill and another ball comes uphill? Have you ever seen that? I haven't.
It's more of an analogy. Imagine rolling a ball downhill generates energy. You could use that energy to pull another ball uphill. In cells, ions moving down their gradient release energy, which is used to move other ions against their gradient.
All right, fair enough. Let's talk a bit about the principles of electrolyte transport then.
All right, electrolytes like sodium, potassium, and calcium move across cell membranes through channels and transporters. This movement maintains electrical and chemical gradients, crucial for functions like nerve impulses and muscle contractions. Transport can be passive, driven by gradients, or active, using energy.
Okay, and what about principles of enterocyte transport? Let's go specific into the GI.
Sure, enterocytes line the small intestine and handle nutrient absorption. They use transporters to move ions, glucose, and amino acids from the gut into the bloodstream. This involves active transport, often powered by sodium gradients, and passive transport for some molecules.
Okay, and are they polarized? Are they?
Yes. Absolutely. They have distinct surfaces, the apical side facing the gut lumen and the basolateral side facing blood vessels.
So what is this apical and basolateral? How does the name relate to the function/structure?
The apical side facing the gut lumen absorbs nutrients, while the basolateral side facing the bloodstream transfers them into circulation. The polarization ensures directional transport.
What is gut lumen?
The gut lumen is the hollow space inside the intestine where digestion occurs. It's where food mixes with digested enzymes and nutrients are absorbed.
Okay, let's see here. Function. Enterocyte, ion uptake, including sodium, calcium, magnesium, blah blah blah. Water uptake, sugar uptake, peptide and amino acid uptake. Okay, a lot of uptake. Disorders, stem aging. Okay, and so when it comes to why is enterocyte transport important?
Enterocyte transport is vital because it ensures nutrients from our diet, like sugars, amino acids, and ions, are absorbed into the bloodstream. This process fuels our body, supports growth, and maintains overall health.
And when you say the apical is facing the gut lumen, can you explain to me the etymology of apical and basolateral? Does basolateral mean lateral to the base?
Exactly. Apical comes from apex, meaning tip or top, referring to the surface facing the gut lumen. Basolateral combines baso, base, and lateral side, indicating the side attached to the basement membrane.
Okay.
Great. Anything else you'd like to dive into?
So, what about I want to find a diagram that shows the enterocytes. Can we talk about tight junctions since they're really related here?
Sure. Tight junctions are crucial structures between enterocytes. They seal the gaps, preventing unwanted substances from slipping between cells. This helps maintain the barrier between the gut lumen and the bloodstream.
So tell me again about the tight junctions.
Tight junctions are protein complexes that create a seal between adjacent enterocytes. They regulate the passage of molecules, maintaining distinct environments on either side of the intestinal lining, crucial for selective nutrient absorption.
And guys, if I show you this picture, I assume this is a... Okay, that makes sense. And so, in the tight junction, what happens exactly?
In tight junctions, proteins like claudins and occludins link adjacent cells, forming a barrier. This barrier selectively allows or blocks molecules, controlling what passes between the gut lumen and bloodstream.
I see. And why is the gut lumen shaped like fingers?
The finger-like shapes are called villi. They increase surface area, enhancing nutrient absorption by providing more contact points for digested food.
I see. So, are the tight junctions more permeable in the proximal small intestine? If yes, why?
Yes, tight junctions can be more permeable in the proximal small intestine. This allows for rapid absorption of nutrients and water early in the digestive process.
Aha, that makes sense. And what about the tonicity of the chyme?
Tonicity refers to the concentration of solutes in the chyme. It influences water movement across the intestinal lining. Hypertonic chyme draws water into the intestine, while hypotonic chyme allows water absorption.
And we've talked about the difference of that. So what is chyme and why is it important?
Chyme is the semi-liquid mixture of partially digested food, stomach acids, and digestive enzymes. It's important because it allows nutrients to be absorbed as it moves through the small intestine.
And how exactly does it affect the directionality of net fluid flux?
Chyme's tonicity affects fluid movement by creating osmotic gradients. If it's hypertonic, water flows into the intestine. If hypotonic, water moves out, maintaining balance and aiding absorption.
So it creates osmotic gradients.
Exactly. The difference in solute concentration between chyme and surrounding tissues drives water movement, creating osmotic gradients.
I see. Okay, now
sense.
the other question I wanted to ask is what does trans and para means in terms of roots?
Trans means across or through, indicating something passing across a membrane. Para means beside or alongside, suggesting pathways next to or between cells.
So paracellular, transcellular.
Exactly. Paracellular transport happens between cells, while transcellular transport occurs through the cell.
And transcellular means that it's going to be against the concentration gradient then, maybe, and also require ATP.
Not always. Transcellular transport can be passive, following a gradient, or active, requiring ATP. It depends on the specific molecules and transporters involved.
But it's more likely to be than the para, right?
Yes, transcellular transport is generally more selective and often involves specific transporters, making it more likely to require energy compared to paracellular.
Okay, that makes sense.
Glad to hear it.
So let's continue a bit more, and then we're going to do a nice switch to another topic. But yeah, so what's a solvent drag?
Solvent drag, occurs when water moves across a membrane and carries dissolved solutes with it. This happens in the intestines when water absorption pulls along ions or small molecules.
So it pulls things with it.
Exactly. As water moves, it drags dissolved substances along with it, aiding in nutrient absorption.
And it follows the sodium gradient.
Yes, often water follows sodium movement. When sodium is absorbed, it creates an osmotic gradient, pulling water along through solvent drag.
That makes sense. Okay, let's put a pause on this topic and let's start talking a bit about the ECG then, shall we?
Sure, let's dive into ECGs.
Alrighty, perfect. Okay, what's an ECG? Why is it important? Why should we care? Think of it from a doctor's perspective, also from a patient's perspective.
An ECG, or electrocardiogram, records the heart's electrical activity. For doctors, it helps diagnose arrhythmias, heart attacks, and other cardiac issues. For patients, it's a non-invasive test that provides crucial information about heart health, guiding treatment and monitoring.
And how do we measure it?
We measure an ECG by placing electrodes on the skin, usually on the chest, arms, and legs. These electrodes detect electrical signals from the heart, which are then recorded and displayed as waves on a graph.
And who built this?
The ECG was developed by Willem Einthoven in the early 1900s. He's credited with creating the first practical electrocardiogram machine and won the Nobel Prize for it.
Interesting. I had no clue. Okay. So, I think it's good to understand the conduction system a bit about when it comes to the ECG. Could you explain us some things about the conduction system?
Sure. The cardiac conduction system is basically the electrical wiring of your heart. It starts with the sinoatrial node, or SA node, which acts like a natural pacemaker. This sends impulses to the atrioventricular node, or AV node, and then down through the bundle of His and Purkinje fibers. This ensures the heart contracts in a coordinated way. It's pretty fascinating how the electrical signals keep everything in sync, right?
Yes,
If
sir.
something disrupts this,
So, what's syncytial then?
sinus rhythm is the normal heartbeat
No,
that
syncytium.
syncytium. In the heart, the term refers to how heart muscle cells work together as a single unit. They're connected by intercalated discs, which allow electrical impulses to spread quickly, making...
So, then in a syncytium we have multiple nuclei and cells, but they're all working as one. It's like the bees in a beehive.
Exactly. A syncytium is a network of cells that share a continuous cytoplasm, meaning multiple nuclei coexist in one mass. This is similar to how bees in a hive operate individually, yet function as a unified colony.
And what about the functional syncytium?
A functional syncytium is when cells are connected and work together so closely they act like one unit. The heart is a great example. Cardiac muscle cells are electrically coupled, so when one cell contracts, the impulse spreads.
Well, excuse me,
making
what's
the
the difference between a syncytium and a functional syncytium then?
Good question. A syncytium typically refers to a structure where cells share cytoplasm, having multiple nuclei in a single mass. A functional syncytium, on the other hand, describes cells that are not fused but act as a single unit through electrical or chemical connections like cardiac muscle cells in the heart.
So the cells, they are not fused in the functional syncytium.
Exactly. In a functional syncytium, the cells remain separate but communicate so effectively that they act as one unit. This is often done through gap junctions, which allow ions and molecules to
But
pass
wait a
directly.
sec, then in a syncytium, what's the difference?
The main difference is in the structure. A syncytium has cells that have fused, sharing a common cytoplasm with multiple nuclei. A functional syncytium involves separate cells that communicate so well that they
And what
function as
in their names clearly showcases this different in structure?
Syncytium comes from the Greek syn, meaning together, and cytos, meaning cell, indicating fused cells. Functional syncytium emphasizes the function, showing cells act together without actually being fused.
Yeah, but syncytium is the same word in both cases. So what exactly in the word functional showcases this distinction clearly?
Functional highlights that the cells aren't physically fused but operate as a unit. It emphasizes their coordinated function rather than their structure, distinguishing it from...
Wow, perfect. And why is this important for us to understand in relation to ECG?
It's crucial because the heart's functional syncytium allows electrical impulses to spread efficiently, ensuring coordinated contractions. This synchronization is what we see on an ECG as the P wave, QRS complex, and T wave, representing the electrical activity of the atria and ventricles.
Okay, and what are some types of cardiac myocyte cells?
Cardiac myocytes include two main types: contractile cells, which make up most of the heart muscle and generate the force for pumping blood, and pacemaker cells, which are found in the sinoatrial and atrioventricular nodes and control the heart's rhythm by generating electrical impulses.
So we have contractile, we have conducting, we have pacemaker, and can you tell us the differences again?
Sure. Contractile cells are the workhorses responsible for the heart's pumping action. Pacemaker cells, found in the SA and AV nodes, set the heart's rhythm by generating electrical impulses. Conducting cells, like those in the bundle of His and Purkinje fibers, transmit these impulses rapidly throughout the heart to coordinate contractions.
Yeah, and I can see how their names relate to their function, which is such an important thing, isn't it?
Absolutely. The names really help us understand their roles: contractile for contraction, pacemaker for rhythm, and conducting for transmission.
So where do the atrial and ventricular myocytes go then?
Atrial myocytes are found in the atria, and ventricular myocytes are in the ventricles. Both are contractile cells, specialized for pumping blood from their respective chambers.
Interesting.
Yeah.
Okay.
Glad it's making sense.
So how are the cardiomyocytes linked?
Cardiomyocytes are linked by intercalated discs, which have gap junctions and desmosomes. Gap junctions allow electrical signals to pass quickly between cells, while desmosomes provide strong mechanical connections. This combination ensures both synchronized contraction and structural integrity.
Okay, guys, the next 5 minutes, I'm going to put the timer, I'm going to do some free association with this piece of information.
Sounds like a plan. Let your thoughts flow.
It's not going to be some crazy free association, but... So...
Go for it. I'm here for all the wild ideas.
So the cardiomyocytes.
Yeah, they're pretty versatile. What connections are coming to mind? Take your time. Feel free to share whatever pops up.
Yeah, I'm just trying to see what's going on here.
No rush. I'm right here whenever you're ready.
So in a myocardiocyte here it says, do we have beta adrenergic receptors and calcium channels and myofibrils?
Exactly. Beta adrenergic receptors respond to adrenaline, increasing heart rate and contraction strength. Calcium channels are crucial for muscle contraction, allowing calcium influx. Myofibrils are the contractile units that generate force. Pretty cool how it all works together, right?
Yeah.
It's a fascinating system.
All right.
Got any other...
let's get back to it. Don't have much to freely associate, to be honest, this time, which is weird for me. Usually I do. Okay, so these cardiomyocytes, they're linked by low resistance pathways associated with gap junctions of the intercalated discs.
Exactly. The gap junctions create low resistance pathways, allowing ions to flow quickly between cells. This ensures rapid and coordinated contraction, which is essential for the heart's function.
So is it the surface area that creates this?
Yes, the intercalated discs increase surface area contact between cells, enhancing the efficiency of signal transmission and mechanical coupling.
And where do we find these intercalated discs?
Intercalated discs are located at the ends of cardiac muscle cells, where they connect adjacent cells to each other.
So they're in the cardiac muscle. Okay. Interesting.
It really is. The heart's design is pretty amazing.
And how is the name intercalated disc related to its structure and function?
Intercalated means inserted between, reflecting how these discs are positioned between cardiac cells. The discs part refers to their disc-like shape under a microscope, which helps connect and coordinate the cell's functions.
Okay.
Makes sense, right?
So in the heart, do we have a... Well, we talked about the AV node and the sinoatrial nodes. We've talked about the valves in other episodes, same with the vena cava. I'm just thinking of the structure of the heart as a whole. We talked about Purkinje fibers a few minutes ago. So, yeah, I'm just wondering, does this in situ break down to atrial and ventricular?
Yes, the functional syncytium does break down into atrial and ventricular syncytia. The atria contract together as one unit, and the ventricles as another, coordinated by the electrical system, including the SA and AV nodes. Exactly. It's all about coordination.
Okay, what about the internodal bundles?
Internodal bundles are pathways that connect the SA node to the AV node, ensuring the electrical impulse travels efficiently across the atria.
Tell me again.
Yep, they're essential for keeping everything in sync.
So what do they do?
They transmit the electrical impulses from the SA node to the AV node, helping to coordinate atrial contraction before the ventricles contract.
And how does their name relate to their structure and function? It's my favorite question.
It's a good one. Internodal literally means between nodes, reflecting their role in linking the SA and AV nodes to facilitate impulse conduction.
True.
Right.
Yeah, now that you point it out, it's obvious. And why is it a bundle?
Bundle indicates a collection of specialized conducting fibers grouped together, emphasizing their unified function in transmitting electrical impulses efficiently.
And what is a bundle?
A bundle is a group of fibers or structures bundled together for a common purpose. In the heart, it refers to specialized conducting fibers that ensure coordinated electrical conduction.
And do we have different kinds of bundles?
Yes, in the heart we have the bundle of His and its branches, including the right and left bundle branches, which help conduct electrical impulses to the ventricles.
Can you explain it to us now? we know that the AV node delays wave excitation from the atrial to the ventricles, and it's basically this is for ventricular filling to be effective. So I understand that, but how is this possible?
The AV node's delay is due to slower conduction through its specialized cells, which allows time for the ventricles to fill with blood after the atria contract. This delay ensures the heart pumps efficiently, coordinating atrial and ventricular contractions.
Yes, but what I'm asking is not exactly this, is it? I'm asking how exactly does it slow things down? That's what I'm asking.
Got it. The AV node slows conduction through a combination of smaller cell size, fewer gap junctions, and more negative resting membrane potentials. This combination creates a deliberate delay in signal transmission.
One more time?
Sure. The AV node's slower conduction is due to smaller cells, fewer gap junctions, and more negative resting membrane potentials. This creates a deliberate delay.
Okay, let me ask you about the ventricular propagation.
Sure. Ventricular propagation is all about the rapid spread of electrical impulses through the ventricles, which is facilitated by the bundle branches and Purkinje fibers.
So what is it?
It's the process where electrical signals travel quickly from the AV node through the bundle of His, down the right and left bundle branches, and into the Purkinje fibers, causing the ventricles to contract in a coordinated manner.
And the Purkinje fibers are bigger.
Yes, Purkinje fibers are larger and have more gap junctions, allowing them to conduct impulses very rapidly to ensure the ventricles contract almost simultaneously.
And so have they grown bigger through evolution?
Likely, yes. Their size and structure evolved to optimize rapid conduction, ensuring efficient, synchronized ventricular contraction.
So, which part of the ventricular wall is depolarized first?
The septum is depolarized first, followed by the apex and then the ventricular walls, ensuring a coordinated contraction that efficiently pumps blood out.
But why does this order is ideal?
This order ensures the blood is efficiently
No,
pushed from
this
the
is
bottom.
don't answer to me generically. You always do this.
Got it. Depolarizing the septum first helps initiate a coordinated contraction sequence, starting centrally and spreading outwards to efficiently eject blood from the ventricles.
Okay. Can you explain this a bit more?
Sure. Depolarizing the septum first anchors the contraction centrally, then spreads to the apex and walls, ensuring the blood is squeezed upward efficiently through the outflow tracts.
Okay, back to the ECG.
Yeah,
Let's
it's
go full circle. So this is a measurement of the heart.
Exactly. The ECG measures the heart's electrical activity, showing how these impulses spread through the heart.
And because the heart is a functional syncytium, it's possible to measure it.
Exactly. The coordinated electrical activity of the functional syncytium produces the distinct waves and intervals we see on the ECG.
Okay. So, what can the ECG diagnose?
The ECG can diagnose conditions like arrhythmias, heart attacks, electrolyte imbalances, and even some structural abnormalities by analyzing the heart's electrical patterns.
Interesting. Okay. And we talked about leads. How many leads do we have?
Typically, a standard ECG uses 12 leads. They provide different views of the heart's electrical activity, helping pinpoint issues in specific areas.
And do things change if we put the electrodes in different places?
Yes, electrode placement changes the view of the heart's electrical activity, allowing each lead to capture signals from different
And why do they change?
Different placements provide unique perspectives on the heart's electrical activity, helping to identify issues like localized damage or abnormal rhythms.
Okay.
It really helps pinpoint problems.
So which is the most common lead?
Lead 2 is often the most commonly used because it gives a clear view of the heart's rhythm and is great for detecting arrhythmias.
So why lead 2 is the most important?
Lead 2 aligns with the heart's electrical axis, providing a clear representation of atrial and ventricular activity, which is why it's so useful for monitoring rhythms.
Interesting.
Right.
So we have 6 precordial ones. Can you tell us more about this?
Sure. The 6 precordial leads, V1 to V6, are placed across the chest to provide horizontal views of the heart, helping to pinpoint issues in specific regions like the septum, anterior, or lateral walls.
And we have 3 bipolar and 3 augmented, and I want you to explain to us how their name relates to their function.
Of course, bipolar leads, I2-3, measure the electrical difference between 2 limbs, while augmented leads, AVR, AVL, AVF, use one limb as a reference point, augmenting the signal to give additional perspectives.
So the bipolar is between an arm and an arm, let's say, whereas the precordial?
Exactly. Bipolar leads measure between 2 limbs, typically arms and legs. Precordial leads are placed on the chest to get a horizontal cross-section of the heart's electrical activity.
Precordial is horizontal section?
Exactly. Precordial leads give a detailed horizontal view of the heart.
And bipolar is between left arm and right arm, let's say?
Yes, for example, lead 1 measures between the left and right arms. Each bipolar lead compares electrical activity between 2 specific points.
And the augmented?
Augmented leads, like AVR, AVL, AVF, use one limb as a reference and amplify the signal, providing unique views of the heart's electrical activity. They complement the bipolar and precordial views.
And why is lead 2 the most important, you said?
Lead 2 is often considered important because it closely aligns with the heart's electrical axis, making it ideal for observing P waves and diagnosing arrhythmias.
Okay. Now, is the ECG the action potential?
Not exactly. The ECG records the overall electrical activity of the heart, while an action potential is a detailed recording of voltage changes across a single cell membrane.
But they are related. For instance, we know that the P waves means the polarization of the atria.
Exactly. The P wave represents the sum of all atrial action potentials, showing atrial depolarization on the ECG.
Yeah. And what about the PR segment?
The PR segment represents the delay at the AV node, allowing the ventricles time to fill with blood before they depolarize.
And tell us about the rest then?
Sure, the QRS complex shows ventricular depolarization, and the T wave represents ventricular repolarization.
Okay, let's put a break into this one and let's go back to our water and salt and all. So, I want to talk a bit about sites for absorption and secretion in the GI with enterocytes.
Sounds good. Let's dive into the GI tract absorption and secretion sites.
Let's see.
Sure, the small intestine is the primary site for nutrient absorption, especially in the duodenum and jejunum, while the large intestine mainly absorbs water and electrolytes.
Okay, so so in the small intestine, um, do the enterocytes uh, practice nutrient absorption?
Yes, enterocytes in the small intestine are specialized for absorbing nutrients.
What
They have
about
microvilli.
in the crypts?
In the crypts, enterocytes mainly secrete fluids and electrolytes, supporting the overall balance and renewal of the intestinal lining.
Why this difference?
The difference supports function. Villus enterocytes absorb nutrients, while crypt cells focus on secretion and regeneration, maintaining the gut's health.
Guys, I need a 5-minute break. I'll be back in 5 minutes with part 2.